Summer is here, and our teammate Ayush is heading to Monaco to watch the F1 race. While booking his trip through an AI agent pipeline, he shares his credit card details and personal details. He then later learns about Monaco's law to be forgotten. He asks the LLM provider to remove his data from the model, and that brings us to model unlearning.
How was the race in Monaco, Ayush?
Yeah, bro, it was a blast, but the EU just couldn't figure it out. They couldn't forget me. There has to be a better way.
Can't we fine tune the model with negative examples?
That's what Microsoft did. I think I was reading their paper. It's called Who's Harry Potter? But it's just not feasible. It requires too much data.
What about a gradient-based method, something like gradient ascent?
Yeah, that's a common approach actually, and it works perfectly well. But do you guys have any ideas on maybe like something that targets the internal representations?
Could we do unlearning on the embeddings or the representation level?
I think that's a promising idea. I think we have got it, guys. Our project builds on previous work called Align-then-Unlearn. The idea here is that true unlearning should change how the model internally represents any concept. We use the RWKU benchmark for this. It contains real-world targets such as Stephen King, which the model needs to unlearn. If Stephen King is the target, the model should forget about Stephen King while still retaining nearby knowledge like facts about other authors or related books. The goal here is precise forgetting with minimal collateral damage to model's
As
broader
Ron
knowledge.
mentioned, we build in the Align-then-Unlearn framework. The key insight is before you can erase something, you need to know what the model's representation of that thing looks like in activation space. So we attach a lightweight embedding prediction module to a transformer layer and train it to decode what the model is about to say from its hidden states. We do this by passing the true next tokens through the embedding layer to get the ground truth embeddings and then comparing those with the model's predictions, and that difference is the training signal. In the unlearning phase, we flip this. Instead of rewarding correct predictions, we penalize them, pushing activations away from the target entity. And this isn't one shot. After each unlearning stage, we realign the module to the updated weights because the model has shifted. And this iterative loop is what keeps Align and Unlearn stable and utility preserving. But the question is, which layers do we target? That's where causal tracing comes in. We run three phases: a clean run to record all hidden states, a corrupted run where we add noise to the subject token and watch the prediction collapse, and then a restore run where we patch back one layer at a time and measure how much the corrected answer recovers. The layer is where the restoration helps most is causally responsible. Our finding is that knowledge localizes to early layers 1 through 9, but intervening at these layers destroys general utility. And intervening at later layers preserves utility but just doesn't unlearn well enough. So, can we have the best of both worlds? That's where our contribution comes in. Simultaneous multi-layer unlearning. Instead of picking one layer, we attach the embedding prediction modules at multiple layers at once, and in our best configurations, layers 4, 15, and 29. During unlearning, all three modules receive gradients simultaneously, and we sum their losses together. This matters for two reasons. First, the early layer handles the forget signal more aggressively. It's close to where the knowledge actually lives. And the later layers anchor general utility because the unlearning pressure is now distributed rather than concentrated at one point. Second, spreading the gradient across layers means that there is no single layer that bears the full update burden, which is what causes catastrophic forgetting in single layer approaches. We were able to get quite positive results using this approach as compared to single layer approaches.
So now let's move on to the results. But before we do that, let's talk about the three metrics that we'll be using to compare our experiments. Unlearning success rate essentially goes through all the prompts that have some facts about a particular entity and counts how many times you made a mistake on them. And the higher you made a mistake, the more you've unlearned. As you unlearn, you end up losing some information and making the model worse, but we want to make sure it's only worse at that particular target. So we want to make sure it still knows how to do math, history, and other types of things. So GUR is a ratio that counts the accuracy on a benchmark like MMLU and compares that between the unlearned model and the original model. The third one is more real world, which basically tests different nuanced prompts that have a little bit more information about a particular entity, like where they were born, and actually checks if the model forgot that as well. So Align-then-Unlearn was kind of a black box technique. They weren't very sure where exactly we should be doing this unlearning. They tried a bunch of different layers. So this got us thinking, what if we zoom into the model to see where this knowledge lies and target the unlearning at those particular locations? And actually running causal tracing on different targets actually biases towards the beginning layers, which makes sense because that's where the foundational knowledge lives. So we took this heuristic and ran Align-then-Unlearn, and we found that we got decent results, but nothing beat actually performing unlearning at later layers. So we took this idea and decided and tried to figure out whether we can do unlearning at multiple different layers at the same time. Maybe a little bit in the beginning, a little bit in the middle, and a little bit at the end. Because that kind of mirrors how knowledge actually lives in our brains and therefore in neural networks. It's distributed. That's what led us to our main method, which is simultaneous multi-layer unlearning. And you can see here that the results across the board are actually better. But they're not when it comes to general utility. Because we're forgetting and destroying the model in more places, it actually becomes worse generally. To address this, we tried to maybe stop the unlearning a little bit early to make it less aggressive, and the results for that were very promising. It ended up doing a lot better in general utility.
Do we go from here? A natural next step would be automating the layer search. Another direction could be folding in tracing into the align and unlearn loop. Finally, maybe Laura can help us navigate the thin line between the model forgetting and it completely collapsing. That's about it from us. Thank you and have a great rest of your day.